Okay, so what we're going to be doing today is we're going to be trying to see whether or not something will precipitate. And up to now, what we've done is we've said, hey, here's a solid, we're throwing that into water, and we're seeing whether or not parts of it will come off and how equilibrium will be established. Now we're going to do the opposite. We're going to take individual ions and we're going to throw them into water and see whether or not there's so many ions in there that the solution saturates and ions pop out. An example of this would be something like this. If I were to put in a solution of water, if I were to drop in Ag plus, throw it into here, and I were to throw in Cl minus into here, there's a KSP that says this. There's a maximum amount of Ag plus times Cl minus that I can have. And if I do the math on that, it's equal to, well, actually the math, if I look up on a table, it's 5.0 times 10 to the negative 3. And that means that these two quantities right here, when these two quantities equal this number or greater, stuff will pop out of solution. That's what we're looking to do today. So what we're going to do is we're going to try and tackle some problems here. And the best way to do that is by actually tackling problems that we are given in the textbook. So I'm going to use this, and they have a handy little flow chart here, if you guys can take a look here on the left. And what we're going to do is we're going to do the problem that they've given us. And there's a couple things we need to be aware of here, and there's a couple of steps that we need to follow when we're solving these problems. First of all, when you take a look at these problems, whatever we're throwing into the solution, I'm going to put a little diagram up here. We want to know whether or not the Q value is going to be greater or equal to the K value. The K value, remember, as we just said a second ago, the K value is the maximum amount of stuff that you can actually include in your solution. So that would be our K value. Our QSP value, or ion product value, that is the same exact formula, but it's how much of each of those two things we actually have. Whatever this number is, we can compare it to this number right here. And if this number right here is bigger than this number, it means that these ions, we have too many of them for the 5.0 times 10 to the negative 3 that the water allows, the overlord KSP allows, which means we'll have a precipitate. If these two numbers right here, if we multiply them together and they end up with a number that's less than 5.0 times 10 to the negative 3, in the case of Ag plus and Cl minus, then nothing will form and we'll end up with ion just floating around because we haven't reached the maximum. So we're gonna do the same thing, and right now we're gonna take a look at two different ions here, and of course they confuse things by adding them with spectator ions. So I'm gonna actually put a line here, and you see how we have Ce and we have IO3 minus. So what we're gonna do is we're gonna throw Ce, which is a 3 plus, we're gonna throw that into water, and we're also gonna throw in IO3 minus into water. Now, those two things together, we're going to multiply them together to get our QSP. Now, our QSP, if we set it up, our QSP is going to be equal to Ce 3 plus, and it's going to be multiplied by IO3 minus all cubed, right? We want to find out what this value is. Now, we know what our KSP value is because they were so kind as to put it right here. I'm going to box this because boxing makes learning easier. Now, what you need to be aware of is when they give us the volume and the molarity of something, what they're really giving us is the moles. So if we take a look at CeNO3 in parentheses 3, and if we're trying to figure out just the Ce3 plus concentration, because we need that concentration to put into here, right? What we really need is we need the moles, or the millimoles, divided by the milliliters, right? Because that's going to give us molarity. So how do we do that? Well, what you need to be aware of is that when we're pouring in, I'm going to make a container to show you the fact that we're actually pouring stuff in, right? We're pouring this in here. They tell us that we have 750 milliliters of our CeNO3. Again, we don't care about the NO3. But don't they also tell us that we have molarity of 4.00 times 10 to the negative 3 molar? So what we do know is this. If they give us the molarity and the volume, wouldn't that allow us to figure out our moles or our millimoles? And why is that a big deal? Well, we're adding 750 milliliters into here. Now you might say, well, okay, don't we already know what our Ce3 plus concentration is? Because don't they tell us right here it's 4.0 times 10 to the negative 3? Yes, that's in 750 milliliters. But what you need to understand here is that we're not just having 750 milliliters, we're pouring that in with a certain amount of IO3. And if you take a look at the IO3 amount, do you see how we have 300 milliliters of the IO3? So when we pour these two things into here, The overall volume is no longer 750 or 300. The overall volume, if we add them together, isn't it 1,050 milliliters? And what that means is this, is that the molarity that we had, which was for 750 milliliters, that's not the molarity that we're gonna have if we have it in 1,050. So there's two ways you can go about doing it. One is you can figure out the moles first and then divide it by the new volume, or you can do it all in one step. I'm gonna choose to do it in the all in one step category, and here's how we'll do that. We're gonna take our molarity and our volume, and our molarity happens to be 1.00, I'm sorry, let me try that one again. 4.00 times 10 to the negative 3 molar. Now, to be really clear, do you understand that molar is equal to moles or millimoles per milliliter? Now, since we know our molarity originally, and now we know the volume that we're starting off with here, which is 750, we can multiply these two numbers by each other, 750 milliliters, and this here is it'd be easier if we converted this to millimoles. We can say millimoles per milliliter, because that's what molarity is, right? We put that on the top, and that's gonna give us our moles. Because if we multiply, or millimoles divided by milliliters times molarity, we're gonna end up with moles. On the bottom, we're gonna add our two volumes together, which is gonna be 750 milliliters plus 300.0 milliliters. And incidentally, I got a little sloppy with my math here. So we have this. And when we do the math on this, on the top, everything cancels out, right? The milliliters cancel out, milliliters cancel out, milliliters. And we end up with our molarity, which is moles divided by liters. And we end up with 2.86 times 10 to the negative 3 molar. So that's our concentration for our Ce3+. When we do the same exact thing for our IO3-, the only difference is that the volume is different, and we also have a different concentration. If you take a look at the concentration here, we have our molarity is 2.00 times 10 to the negative 2 molar, and our volume is 300 milliliters. Again, if we multiply our molarity by our volume, and we could make this, we're gonna take this and convert this to millimolar if we wanted to, isn't that still gonna be divided by the same number, 750.0 milliliters and 300 milliliters? Again, you might find it easier to multiply these two things together and end up with your millimoles, and then divide that by the overall volume, because that's essentially what we're doing right now. We're canceling out these two units because molarity, in this case, is millimoles divided by milliliters. So when we do the math on this, we're gonna get the same sort of deal, and in this case, the actual value we're gonna get is 5.71 times 10 to the negative 3 molar. Now, if we solve for Q in this, our Q value is actually gonna be equal to, and let's set up our problem. We're just gonna plug in our values up here. If we plug in the values into our problem, we're gonna end up with 2.86 times 10 to the negative 3, all times 5.71 times 10 to the negative 3, all cubed. Yeah? Do the math on that, and we're gonna end up with our Q value being 5.3 times 10 to the negative 10. When we do that, we can take this number right now, and we can compare it to our KSP. Our KSP is 1.9 times 10 to the negative 10. If we take a look at this, we have 5.3 times 10 to the negative 10 versus 1.9 times 10 to the negative 10. Our Q value is bigger than our KSP value. And because of that, our Q being bigger than our KSP, it means we have more product in our solution, if we take a look at our overall Q value here, than we should, which means that a precipitate will definitely form. So in this case here, we definitely have a precipitate that is forming. Yeah? Okay. Now, what they also like doing is they also like doing this. They like giving us problems where they say, yeah, okay, tell us that a precipitate forms, but also on top of that, tell us how much of the ion is going to be left over. So what we're going to do with this is we're going to actually solve a problem to work the same thing out. But there are 3 steps, and I've jotted them down in your notes here so you're aware of it. But first things first, in all problems, whenever they give us ions that they're throwing into something, so let's say we have our little container like we did before, and we're going to throw in 2 different ions in here. The first thing we have to determine is whether or not they're going to form a precipitate, and that is solving for Q. So our first step is solving for Q and comparing it to KSP, which is the problem we just did. Then what we're going to do is we're going to do a stoichiometry problem. This is where it gets a little bit tricky. And we're going to see how much is left over of one of the two ions that does not form precipitate. Because whenever you put two things together, let's say I have 10 millimoles of Ag plus and I have 8 millimoles of Cl minus. I don't know why I didn't put the Ag plus first and the Cl minus second. But if I put these two together, you realize that the overall stoichiometry is going to be this. 1 mole of Ag plus 1 mole of Cl minus will give us 1 mole of AgCl. Agree? But if I'm starting with 8 millimoles of this and I'm start with 10 millimoles of this, will you agree with me that when everything's said and done, I'll have 0 of the Cl minus. But then when I have 2 millimoles of the Ag plus still just sitting there, agree? So what we have to do is whenever we dump in stuff, we have to see how much of one of those things is left over, because after we do our stoichiometry and we determine what's left over, we're then going to do a regular ice problem where we start putting things back into the equilibrium from the solid and seeing whether or not, or seeing how much is left of both of these things after the fact. Now, that seems a little bit confusing, so the best way to solve it, and I apologize for how verbose that was, we're gonna actually try a problem on this. So let's try this problem. This is in the textbook, and I even gave you the example here so you guys can look it up on your own and see the math that was done. But let's walk through these steps, and we're gonna do the exact same problem that we did before. And the first step here is this, recognizing what two things are we putting together. So if you take a look at this, do you see how they give us Mg and they give us NAF? MgNO3 and NAF. What that really means is this. What are the two things we're concerned with? We're concerned with Mg2 plus and we're concerned with F minus. Does that kind of make sense? And what we're going to do is we're going to put both of those things into a container. Yeah? And we're going to try and determine whether or not this Mg2 plus and this F minus, the amount that we put in here, whether or not the Q value of that is going to be greater than or less than our K value. Now, they give us the K value for MgF2, right? So what we're going to do right now is we're just going to set up our problem and determine whether or not our QSP, and I'm going to write our QSP equation here, wouldn't that be Mg2 plus, 2 plus times F minus all squared. So if we have our concentrations of these two things, can't we plug it in here for our QSP? And that's what we're gonna do right now. Same sort of problem as we did before. I'm gonna set it up into two different steps. I have my Mg2 plus concentration. And the way I'm gonna get that is this. Don't I again have my molarity and my volume? So I have my molarity and my volume, I can set it up in a molarity type problem. So I can go on the top, I can go molarity, which is, let me remind you of this. Again, don't we want to have on the top our moles or our millimoles, right? And on the bottom, don't we want to have our volume? So molarity is always equal to moles over volume. We're going to be able to figure out our moles from our molarity and our volume originally. The volume on the bottom is our overall volume. And that's when we've added in the amount of F minus and the Mg2 plus into the solution. So when we actually plug the numbers in, we get this. Let me remind you again that this 400 milliliters we got from adding the 150 milliliters here and the 250 milliliters here. So we have this. We're gonna do the exactly same thing for F minus. So now we have our two concentrations of Mg2 plus and our F minus. So we're gonna plug that back into our Q expression, which I'm gonna box right here. I don't wanna write it again, so I'm just gonna write my QSP. And let me point out here that this is squared right now, and that's a big deal. And when we compare that to our K value, which happens to be 6.4 times 10 to the negative 9, 1.46 times 10 to the negative 5 is significantly bigger. So since our QSP is bigger than our KSP, we know that we're going to have a precipitate form. The next step is to say, well, what would happen if we ran both of these to completion? And so aren't we really just doing this? This is the equation we're running. We're running Mg2 plus and we're running two F minuses all together, and together they're forming MgF2. That's what we're doing when we're throwing this in here, if we are forming a precipitate. And we know that our QSP is bigger than our KSP, so we are gonna form a precipitate. So we're just gonna do a before, we can do a before and a change and after, a BCA, but we could just do this. couldn't we take the molarity and the volume of the Mg2 plus, which we started with in this problem, and wouldn't that be 150 times whatever? Wouldn't that be 1.50 millimoles? If you're wondering how we got that, it's by multiplying 150 by 0.01. Similarly, for the F, we have 25 millimoles. And if you're wondering again how we got that, again, take the 1.0 times 10 to the negative 5, which is our molarity, and we multiply it by 250 milliliters. Yeah, so we get 25 millimoles. Again, we don't care what's actually being formed here, but if we do our change, since this is a 1 to 2 ratio right here, would you agree with me that we're gonna lose 1.50 here, right? But then won't we lose 2 times 1.50 here? And the end result will be have none of this, and then won't we have 22.0 millimoles of F minus still sitting in solution when all of our Mg2 plus is being used? So we know that when this starts to precipitate into our solution, right? When it starts to precipitate out, we're gonna have 22.0 moles, millimoles, not moles, millimoles of F minus still floating around in here when we start forming our MgF2. Now, what do we do with that, and how does this then transcend into an equilibrium problem? So let me show you this for just a second. Let me remind you. The 3 steps that we're gonna follow every single time are these 3 steps. Step number 1, we're gonna see whether or not our Q is greater than our K, and we have. Step number 2 is we're gonna do a stoichiometry problem to determine how many millimoles of each ion we have at the end. And we've just done that, and we've determined that we have 22.0 millimoles of F minus sitting there at the end doing nothing. Now, our last step here is this. We want to then figure out an equilibrium problem. Now, it should be noted here, just having 22.0 millimoles is not very useful in an equilibrium problem, because if I were to write an actual equilibrium expression, a KSP problem for this, wouldn't our KSP problem look like this? Wouldn't it be KSP is equal to Mg2 plus, right, times F minus squared, right? But if I were to write the actual equation out, the equation is this. It's MgF2 as a solid, and both of these are aqueous. Now watch, and this is kind of a big deal on this. In order to be able to solve this problem, we know what the KSP problem is, right? Our goal is to figure out what our equilibrium values are, so can't we do an ice problem? So if we're doing an ice problem, then we need to know what our initial concentrations are of both these things. Now, because we know that we had an excess, and let me point this out to you, we had an excess of F minus, but that's in millimoles, right? So I have 22.0 millimoles of F minus are left sitting here, right? But I want to convert that into molarity. So in order to do that, mustn't I divide that by my overall volume, which in this case, isn't it 400 milliliters? So if I divide 22.0 millimoles by 400 milliliters, I'm going to end up with 5.50 times 10 to the negative 2 molar. And so when I'm doing my initial quantities here, we don't care about this step right here. But we do care that we have 0 of this because it's been all used up when we formed the MgF2 in the beginning. And we're going to have 5.50 times 10 to the negative 2 molar here. Now, what's my change going to be? Well, we have solid being formed, so won't we lose X from this, right? And then if that happens, won't we end up with X here? And when we end up with 5.50 times 10, let me just scratch that because that's a terrible skipping of change. Wouldn't the change here be X and then 2X? I kind of jumped to the equilibrium state. And then in equilibrium, wouldn't this be X and wouldn't this be 5.50 times 10 to the negative 2 minus 2X? And if we put all that back into our equilibrium expression, what we have is this. And again, I'm just putting the numbers back in here. My KSP value is 6.4 times 10 to the negative 9. I got that from the beginning of the problem. And that's going to be equal to my Mg2 plus concentration times my F minus concentration all squared. And if I plug these numbers in, I'm going to end up with this. I'm going to end up with 5.50 times 10 to the negative 2. That actually belongs there, and I kind of flubbed. Minus 2x, and it's all going to be times x. Now, one of the cool things about these problems is that because this is this is a really small K value, we can get rid of this 2x compared to this 5.5 times 10 to the negative 2. And when we set that up, what we're going to end up with is our x value in this is going to be equal to, and if we solve all this out, our x value is going to be equal to 2.1 times 10 to the negative 6 molar. Again, this is ugly, so if you want to see a better version of this, you can look in the textbook. But if I had to do this again, I would do it like this. Because in all of these cases here, I realize I put a minus x here, and it should be a plus x and a plus x. That's me just trying to get through this quickly so this video isn't interminably long. But what I do know is this. At equilibrium, isn't my x value, wouldn't that be equal to my Mg2 plus concentration? Yeah. And wouldn't my equilibrium value for my F minus, wouldn't it be 5.50 times 10 to the negative 2 minus 2x? Well, didn't we already, if we do the math here, and if I were to plug this value in here, and I multiply 2 by 2.1 times 10 to the negative 6, I hate to break this to you, but this is going to be nothing. And therefore, my F minus concentration is going to be 5.50 times 10 to the negative 2. That will be my F minus concentration. So hopefully this has been helpful. Again, write any questions down or any problems you had, and we'll go over this stuff in class. Thanks so much. Bye.